Welcome to our second spotlight on statistics. This one, we're going to discuss z-scores, standardized scores, which are basically just a form of z-scores, and then we're going to look a little bit at the normal distribution, which is basically the most common uh, distribution we have, and that's where z-scores come from. They're on the normal distribution. Okay, before, in a previous video, we looked at measures of center, which are things that measure the center of your data, like the mean, the median, and the mode. And then we also looked at standard deviation as a measure of spread. Well, now we're going to move on to these ideas of a z-score. And here's your formula down here. It's very simple. A z-score is just x minus x bar over SD. What does this mean? Well, x is your data value, so whatever you're trying to compute a z-score for, that's the value that you use. And then x bar, that's the mean, so that's the average of the set of data that you are pulling from, and then SD just means the standard deviation of that set of data. So let's say you get a 63 on a test. You want to know, is that good or bad? Well, it all depends on what's the average and what's the standard deviation, right? I mean, it could be 63 out of 63, and then obviously that's really good. Could be 63 out of 500, and that's obviously not very good at all. But maybe 63 out of 500 is still pretty good because maybe the average is only 50, right? So it all depends on what's going on. So let's assume that the mean on this score, on whatever this test is, the mean is 51. And so now you can see that you're 12 points above the mean, right? Because 63 minus 51 is 12. But again, is that good or bad, right? Does that put you way at the top? Or do most people score 12 points or more above? So we need to know what is the standard deviation of scores. So let's assume the standard deviation. Remember, the standard deviation is kind of the average distance from the mean. Let's pretend that the standard deviation for this set of data is 5. So now you have a score that's 12 above. That's 2.5 standard deviations above. That's pretty good. Now you might not know that, but 2.5 is pretty good. So in fact, if you do the math, 63 minus 51 divided by 5, you get an actual answer of 2.4. So your score on this test of 63 has a z-score of 2.4. And the z-score just means how many standard deviations you are above or below the mean. So if you have a z-score of negative 2.4, that means you're 2.4 standard deviations below the mean. And if you have a z-score of positive 2.4, as you do in this scenario, you're 2.4 standard deviations above the mean. And you might go, okay, well, what does that mean? Well, think of a standard deviation as a unit of measure, like a foot or a yard or a meter, right, or a centimeter. A standard deviation is just a unit of measure. So you're 2.4 centimeters above the mean. You're 2.4 inches above the mean. And depending on the data you have, that unit of measure could be different, right? It could be really small, like a centimeter, or it could be really big, like a yard. So you're just 2.4 measurements above. That's what a standard deviation is. Okay, let's look at the example that we just kind of computed, but with new numbers. So now we have an average of 75, that's our mean, and we have a standard deviation of 4.74. We can now compute z-scores for all of these things. Your z-scores will always have a mean of 0 and a standard deviation of 1 because of what we're doing, because of the math where we're subtracting the mean from everything and then dividing by the standard deviation. It ends up giving us an average of 0 and a standard deviation of 1. So these numbers down here are really just kind of like ratios of these numbers up here, right? A score of 75 is the same thing as a z-score of 0. And a score of 72 ends up being negative 0.63, or a little bit more than half of a standard deviation below, just like 81 is 1.27 standard deviations above. Okay. There are other common standardized scores, not just z-scores. Z-scores is kind of the most common, but we also do t-scores, which come on the t distribution, and all sorts of other things. But z's and t's are the two that come up the most. T-scores center at 50 and have a standard deviation of 10. NCE scores also center at 50, but spread out more with a standard deviation of 21. These are just different types of scores. IQ scores have an average of 100 and a standard deviation of 15. And then SAT scores, I'm assuming this is the new version of SATs because the old version of SATs had a different average. But the new version has an average of 50 and a standard deviation of 100. And we can put all that stuff together and kind of see how they all compute. And you can actually compute all of these based on z-scores with simple conversions, right? So you take your z, you multiply by your standard deviation, you add the average to it, and that gives you the new score for that new set of data, right? So you can take a z-score on this test, whatever it is, multiply it by 15, add it to 100, and that tells you what your IQ is. So if this test has an average of 75 and you got an 81 on it, that means your IQ should be roughly 119. So z-scores basically enable us to compare data from two different things, right? You could compare someone's IQ score to the score they get on an SAT. Even those two things have hugely different ranges, right? The IQs, like we said, have an average of 100, a standard deviation of 15. The lowest IQ, I think, is about 40. I think is about as low as it gets, and if you're 40, you're considered extremely mentally challenged. And then the highest IQ I think ever recorded is like 190, 200, something like that, right? I could be way off, guys, but it's a pretty small range. Whereas SATs, right, the lowest SAT score, I believe is, well, it used to be 200. I think it's now 300. And then the highest is 2400. So there's a much bigger range. But we can use z-scores to kind of convert the two and then be able to compare the two. And the same thing goes with the ACT. If you ever took the ACT, and I didn't take it, so don't quote me on this, but I think ACTs, they're much smaller. They range from like 1 to 40 or something rather than 300 to 2400. But you can convert both of them to z-scores and be able to compare an ACT score of blank to an SAT score of something else and see which one is better. Okay, this is the normal distribution, and this is where z-scores come from. If you have a z-score of 0, you're right in the middle. This is the average, you're right at the mean, and you'll notice that a normal distribution is centered. It's symmetrical. There's just as much area to the left and to the right. This 0 represents the mean. It also represents the median, right? Because 50% is above, 50% is below. And because it's the tallest part on our distribution, it's also the mode. So z-scores live on a normal distribution where the mean, median, and mode are all the same. These distributions are standard. No matter what you're doing, when you convert something to z-scores, you're converting them to this distribution. And one standard deviation, one z-score, right, always captures 34.3% above, one z-score below, 34.3% below, and so on and so forth. So normally we kind of memorize these as 34, 14, 2. We round them. So if you go one standard deviation in each direction, you get 34 plus 34, which is 68. Right? If you go two standard deviations in both directions, that's roughly 95% of the data. And if you go three standard deviations in both directions, that's roughly 99.7. So we also talk about 68, 95, 99.7 as being how much of the data is within one standard deviation, i.e. one z-score in both directions, two z-scores, and three z-scores. So here's another example where we can use this to actually compare data. So for instance, it says here 11,000 household incomes in the US had a z-score of 92. That means that they're way up here. And a z-score of 92 means you're way, way up here, right? See, here's the 99th percentile right here. So a z-score of 92 puts you way up in the 1%. Those are people that are, making billions. By comparison, if a woman had a height that was 92 standard deviations above the mean, i.e. she also had a z-score of 92, that would make her 27 feet tall. So that kind of tells you how far out from normal it is to be 92 standard deviations above. So just remember 68, 95, 99.7, and that'll help you figure out what percentages are within so many standard deviations of the mean. And that's pretty much everything for this video.